techniques. In this video, we're going to be talking about a particular technique called crystallization. And as the name suggests, crystallization is all about the formation of crystals. What exactly are crystals? Well, crystals are solids. And crystals, not all of them, but some of them, some crystals are able to dissolve. And when something dissolves, you might already know. For example, if a salt crystal dissolves in water, it kind of just disappears. You can't just reach back into the water and try to grab the salt crystal out. It's dissolved. So what is crystallization for? Crystallization helps us get back solids that have dissolved into, let's say, liquids. To further dive deeper into crystallization, let's start off with an example. Here I have a beaker of water. Water is a compound called H2O. And let's say I want to dissolve something very familiar to you. Let's say I want to dissolve table salt. Table salt, for your information, is also a crystal. It is also a compound. And this compound is called sodium chloride. This is the chemical symbol for table salt. Table salt is a crystal. It is a solid. If I were to zoom in and have a look at the particles, you find that the particles are very neatly arranged in an orderly fashion, very closely packed. And this particular crystal of table salt, and this crystal is able to dissolve. If I were to dunk it into water, give it a good stir, you find after a while the solid crystal no longer exists. If something is able to dissolve in another liquid, we refer to this thing as a solute. Oops, I think I spelled solute wrongly. I should remove this L over here. Solute. If something is able to dissolve the solute, we refer to it as a solvent. We've encountered this word before in chromatography, solvent. Solvents are able to dissolve substances. The thing that dissolves in a solvent is the solute. And when a solute and a solvent comes together, we refer to this as a solution. And so what I have in this beaker, this is a solution of salt water. What does this all look like if I were to zoom in? Okay, if I were to zoom into this beaker, this is what you see. You will see that the solute particles are no longer very closely packed to each other in a solid state. Instead, they have separated out from each other. There's a lot of space between them now. But it's not empty space. In between the solute particles, you find solvent molecules. This is the water molecules, the solvent. So in a sense now, the solute particles are intermingling with the solvent. They have dissolved. They are no longer closely packed in an orderly, uniform fashion. That's why it's no longer in its solid state. It is now intermingling with the solvent. This is a little bit problematic now. If I were to ask you now to fish the salt crystal back out from the solvent, how in the world are you going to do that? You can't just reach your hand in and try to grab each individual solute particle. It's just not possible. It's really, really, really small. So this is what crystallization is for. The aim of crystallization is to help us get all the solute particles back out from the solvent. But how are we going to do that? Okay, now let's go into some of the apparatus that will help us achieve that. What can help us achieve that? We need several things. Here, I have what I call an evaporating dish. Evaporating dish. Okay, an evaporating dish, this is the 2D version. It's a side view. If I were to look at it from a 3D perspective, an evaporating dish is like a bowl that's made out of ceramic. It's able to withstand high amounts of heat without breaking. This is a tripod stand. what you put your evaporating dish on, so they can prop it up like on a table. This is a Bunsen burner where the heat source comes from. And inside the evaporating dish is where I'm going to perform a little bit of magic. Okay, I want my solute back from the solvent. First thing I'm going to do is I'm going to dunk the solution. I'm going to pour the solution into the evaporating dish. And so what you find here, this is the solution. The solution contains both the solute and the solvent. It is now inside the evaporating dish, and I'm going to turn up the heat. Here I've turned on the Bunsen burner, and now it's beginning to heat up the solution. Let's look on a microscopic level what this looks like. Here you find, again, the solution. This is the solution. In the solution, you find the solute particles and also the solvent particles. As I heat up this entire mixture, something quite interesting will happen. We learned in our previous chapters that when things heat up, they gain kinetic energy. When they gain kinetic energy, they move faster and further apart. Here I've highlighted one single water molecule. It's moving faster. Okay, it's moving faster and further apart. It has gained more kinetic energy. And when it has enough energy, it will pull itself away from the other water molecules and start to go into its gaseous state. No longer closely packed. Okay, this is one water molecule that has gained enough kinetic energy to leave the liquid state of the water molecules. Right? It's, in a sense, now it's evaporating away. They're gaining enough energy, kinetic energy, separating away from the bulk of the water molecules in liquid state. If I allow this to continue on for a longer period of time, this is what you see. A lot of the water molecules have evaporated away or boiled off as I continue to heat up the solution, because they gain kinetic energy. So in a sense, what I'm doing here is I am removing the solvent. By heating the solution up, the solvent is boiled away, is boiled off, or is evaporated away. And what stays behind are the solute particles. Here you see the solute. You notice that the solute particles don't evaporate away, they don't boil away. Remember, earlier on, one of the first few lessons, I said that a salt has a boiling point of 801 degrees Celsius. It's crazy high. And so you expect that I need a lot of thermal energy for salt to really boil away. However, water has a boiling point of just 100 degrees Celsius. That means to say when I hit 100 degrees Celsius, all these water molecules, they will begin to boil off. That's normal. The salt particles, they stay behind because its boiling point is really high. And if you notice, because it stays behind, this solution now gets really crowded. Right? If I were to compare these two boxes here, look at A and look at B. Notice how B is so much more crowded. And there's a lot more solute now compared to solvent. Right? And this is what we want. We want to heat it up. We want to heat up the solution until we reach such a point. Eventually, you'll reach a point where something amazing happens. If I were to take a glass rod, a very cold glass rod, and I were to dip it into the evaporating dish, when it's so crowded, when the solution is so crowded, something amazing will happen. If I were to dip it in, and then I were to take the glass rod out, okay, I dip it into the solution, the solution that's now really crowded, and then I take it out, you find something interesting happen. You find that at the edges of the glass rod, small little crystals will begin to form. Small little salt crystals will begin to form. If you see salt crystals begin to form on the glass rod as it cools down, we say that now this solution is saturated. Okay, we say that this solution now is saturated. Okay, this solution is saturated. What does saturated mean? Saturated mean that there is a lot of something. So let's say, for example, if you sit for a lesson for too long, your brain is saturated with information. That means you have a lot of information in your head now, too much. Same goes here. If I heat up a solution for a very long period of time and the solvent evaporates or boils off, it becomes saturated with the solute, right? And when we see crystals begin to form on a glass rod when we dip it into the solution, we know that it's now saturated. This is at this point, at this period of time when the crystals start to form, we call this the saturation point or crystallization point. This is the point in time where we know that the solution is saturated. Okay, so I say again, a saturation or crystallization point is the point in time that we know that the solution is saturated. How do we know? We know if, well, when we dip a glass rod into the solution and we pull it out, crystals begin to form. Now we know that the solution here is crowded enough. Why do we want the solution to be crowded, right? Why do we want it to be filled and saturated with solute? Because something very interesting happens. When it gets too crowded, when it becomes really saturated, you find that there's less and less solvent molecules between each solute particle. Okay, notice now, less space between them now, right? Less space between each solute particle because there's less and less solvent. And something amazing happens when there's less space, when there are less solvent between each solute particles. There's a much higher chance, let's look at these two over here. There's a much higher chance that the solute particles can come back together again. Okay, let's find some more. Look at this solute particle. Now it's so close to each other, they can come back together again because the solvent molecules have boiled off, evaporated away. It's coming back together again. It's coming back together again. Let's see any more. Okay, look at this one. This one is coming back together again. So this is why we want to evaporate or boil off the solvent. When there's less solvent, the solute no longer is able to dissolve. It starts to come back out as crystals. Right? They are coming back in an orderly arrangement. I'm just finding all the solute particles. They are very close to each other now. Okay, they are coming back in an orderly arrangement into what we know of as a solid state. Okay, and imagine we continue. These solute particles continue to come together. Eventually, they'll form back a crystal. Crystal is a solid, right? When there's less and less and less solvent, there's a higher chance of the solute particles coming together, and it forms a solid again. The crystal has formed, right? This is beautiful. We've got back what we want. This is the solute, but in crystal form now. A crystal has reformed. Crystals can only form after the solution has reached the saturation point, as we mentioned earlier. Okay, the solution needs to be saturated, then the crystal can reform. Okay, and so you'll find after the saturation point, if you let the solution cool down to room temperature, crystals begin to form at the very side of the evaporating dish. Okay, I'm trying to draw crystals over here. They begin to form back. Because it's too crowded now, they can come back into solid state. And that's great. I'm beginning to get my salt crystal back. The final step, just to really get the crystal out, is you notice that there's still leftover water. Okay, there's still leftover water over here. We have to get rid of the water. Once we get rid of the water, then all I'm left with is the crystal. Okay, so over here, how am I going to get rid of the water? You will see inside your textbook it says that it uses filter paper. The paper just helps to, if I were to dab it with filter paper, the filter paper just helps to absorb away the water molecules. Okay, so the water molecules, the remaining of it, will get absorbed away by the filter paper. And then all I'm left with is the salt crystal. Brilliant. Okay, all I'm left with is the salt crystal. And that's what crystallization is. I've gotten back my salt crystal. And some of you may be wondering, Mr. Tan, why don't I just evaporate all the water off? Right? Why do I evaporate all the water off such that I'm just left with the salt crystal? Why do I leave some water behind? Well, we tend to leave some water behind because sometimes some crystals will break down if I don't have any water behind. If I just evaporate all the water away and the heat directly heats up the crystal may end up breaking down into its elements. So that's why we tend to not boil off all the solvent away. We leave some solvent behind, and then after that we dry it up. We dry the crystal up. Okay, that way we won't break down the crystal with extreme heat. Alright, so that's what crystallization is. To summarize, we use crystallization when we have dissolved a particular solid into a solvent. Okay, we refer to the thing that can dissolve in the solvent as a solute. Solvent is the thing that can dissolve the solute. What we form is a solution. If we want to get the solute back out, what we do is that we boil the solution and let the solvent evaporate away or boil away. When enough of the solvent or has evaporated or boiled away, what we left with is a saturated solution. Saturated solution contains a lot of solute now. We refer to this point where the solution is saturated as the saturation or crystallization point. This is the point that we know that the solution is saturated. And from there on, crystals can start to form. Because there's less solvent, the solute particles are more able to come back together to form a solid state, and crystals form. And the last step is just really to dab away and remove the remaining water such that I'm just left with the crystal. Pure crystal. This is pure table salt. Right? And that's all for crystallization. This is a rather long video, and some students find this very tough. But actually forming crystals is really fun. If we get to do it one day, we really should form some crystals in the class together. Thank you.